There is a room in a building in Shenzhen that America does not talk about. Not because it is classified, not because what happens there is secret, because what happened there over the past 4 years was so far outside what the people who designed the restrictions placed on China believed was possible, that acknowledging it requires acknowledging something uncomfortable about the assumptions those restrictions were built on. In that room, engineers at Huawei were handed a problem that the global semiconductor industry considered unsolvable without specific tools that America had ensured they could never access. The engineers were told, in effect, that without those tools, the ceiling on Chinese chip development was fixed, that the gap between what China could build and what the West could build would widen permanently, that the most important technology competition of the current era was over before it had fully started. The engineers did not accept the ceiling. What they built instead is not a better version of what the restrictions were designed to prevent them from building. It is something the restrictions were never designed to stop because nobody designing them believed it was possible to build it. Today, we are going to go through exactly what they built. Not the version that fits in a headline, the full version, the technical reality behind the announcement, the specific numbers that matter and what they actually mean, the genuine obstacles that remain, and the question that sits underneath all of it that nobody in the public conversation has fully answered yet. By the time we finish, you will understand why this story is not about one company or one chip or one country's technological pride. It is about something considerably more important than any of those things. It is about whether the theory that controlled technology access can permanently determine the outcome of technological competition is actually true. The answer that is emerging from that room in Shenzhen is making a lot of people in Washington very uncomfortable. Stay with this. The story gets more significant at every layer. Hit the like button right now before we go any further. The research behind this goes considerably deeper than most coverage of this subject, and every like directly helps it reach people who want to understand what is actually happening rather than what is easy to report. Subscribe and turn on notifications. This is a story that is going to keep developing, and you want to be there for every chapter. Let us go. Start with why America was so confident. The confidence was not casual. It was not the kind of overconfidence that comes from underestimating a competitor. It was grounded in a specific and sophisticated understanding of how semiconductor manufacturing actually works, and why certain pieces of equipment occupy positions of irreplaceable strategic importance. For 60 years, the path to more powerful chips ran through a single technical achievement repeated over and over, making transistors smaller. Smaller transistors meant more transistors in the same space. More transistors meant more computing power. More computing power in the same physical area meant lower cost per unit of computation. The cycle repeated with a consistency that made it look like a natural law rather than an engineering achievement. Gordon Moore noticed the pattern in 1965 and described it. It became Moore's law, and it held with variations and occasional stumbles for long enough that the entire global technology economy was built around the assumption that it would keep holding. The way engineers kept making transistors smaller was through lithography, a process of using light to project patterns onto silicon at scales so small they are measured in billionths of a meter. The physics of light sets the fundamental limit on how small those patterns can be. To make smaller transistors, you need shorter wavelength light. To produce shorter wavelength light, you need more energy and more precise equipment. Over 60 years, the progression went from ultraviolet light to deep ultraviolet to extreme ultraviolet. Each step required more sophisticated machinery. Each step produced a generation of chips that outperformed everything that came before. The machine at the end of this progression is made by a Dutch company called ASML. It is called an EUV lithography system. It produces light with a wavelength of 13.5 nanometers by firing a laser at droplets of molten tin falling at 50,000 per second. The laser blast turns each droplet into a plasma that emits the required wavelength. That light is guided through optical mirrors, machined to a precision where a single atom of surface contamination would compromise their performance. The entire optical path operates in a vacuum. Each machine costs approximately $200 million. ASML produces fewer than 60 per year. Every unit goes to TSMC in Taiwan, Samsung in South Korea, or Intel in the United States. These three companies use EUV to build the chips that power everything at the frontier of modern computing. When America designed the export restrictions on Huawei and on SMIC, the Chinese manufacturer that makes Huawei's chips, the strategic logic was clear. Without EUV, you cannot print advanced transistors. Without advanced transistors, you cannot build advanced chips. Without advanced chips, you cannot compete in artificial intelligence, in high-performance computing, in the applications that will determine economic and military advantage for the next several decades. Control the machine, control the chips, control the future. That was the theory. And the theory was not wrong about the importance of the machine. It was wrong about something else. Before we get to what Huawei built, let us acknowledge what they tried first. Because the first response to the restrictions was not the announcement that stopped the industry cold. The first response was something that was impressive enough on its own terms that it should have been a signal about what was coming. SMIC, working with the tools they were allowed to keep, pushed an older generation of lithography technology further than the industry believed it could go. The machines they were using, called DUV systems for deep ultraviolet, were designed for an earlier era of chip manufacturing. The conventional wisdom held that they had a ceiling, a point beyond which the physics of their longer wavelength light simply would not allow further miniaturization. SMIC found a way around the ceiling through a technique called multi-patterning. Instead of printing a chip pattern in a single lithography step, you decompose the pattern into multiple, simpler sub-patterns. You print each sub-pattern separately, align them with extraordinary precision, and combine them to produce the complete design. The alignment between layers must be accurate to within a fraction of a nanometer. A single misalignment ruins the chip. SMIC pushed this approach further than any independent expert had believed was achievable, and produced chips roughly equivalent to a 7-nanometer manufacturing process. The result was a Huawei smartphone that benchmarked considerably better than the restrictions were supposed to allow. The global semiconductor industry took notice, but Huawei and SMIC knew this was not the long-term answer. Multi-patterning adds cost, complexity, and yield challenges with every additional step. There is a ceiling on how far the approach can go, and that ceiling was approaching. So Huawei's engineers stopped trying to push through the ceiling and started asking whether the ceiling was actually made of the material everyone assumed. The question they arrived at changed the frame entirely. What if the path to more powerful chips does not run through smaller transistors at all? This should sound wrong. The entire 60-year history of semiconductor progress was built on the principle that smaller transistors equal more powerful chips. If that principle is not the fundamental truth everyone assumed it was, then a significant portion of the last 6 decades of engineering effort was organized around a simplification that hid something important. Here is what was hidden. In a modern computing system, more than 80% of energy is consumed not by computation, but by data movement, not by the transistor switching, by the signals traveling between the transistors. The thinking is not the bottleneck. The communication between the thinkers is. A chip is not just a collection of transistors. It is a city compressed to the size of your fingernail with hundreds of billions of workers. The transistors, connected by a network of metal roads that stretch across more than 20 layers within the chip. Every time information needs to move from one part of the chip to another, it travels through those roads. And those roads create 2 problems that grow worse the longer they are. The metal resists the flow of electrical signals in the same way a narrow pipe resists the flow of water. And the metal acts like a tiny capacitor, a miniature rechargeable element that has to charge up every time a signal enters it and discharge when the signal leaves. The combination of these effects is called RC delay, and it is the reason that the clock speed of processors, the metric that most directly reflects how fast a chip can think, has barely increased in 15 years, even as transistor counts have continued to climb dramatically. We are not limited by how fast the transistors can switch. We are limited by how fast signals can travel between them. The transistors are ready and waiting. The roads between them are the constraint. Huawei's engineers recognized something in this picture that nobody had seriously acted on at this scale before. If the problem is distance and the energy and time consumed by that distance, then the solution does not have to be smaller transistors. The solution could be shorter distances. And the most dramatic way to make distances shorter is not to rearrange things on a flat surface. It is to eliminate the flat surface constraint entirely. It is to fold the chip. The concept sounds almost absurdly simple when you first encounter it. Take a piece of paper with text on it. The words at the top left corner are separated from the words at the bottom right corner by the full diagonal length of the page. Now fold the paper in half. The same words are now separated by nothing but the thickness of the paper. The words did not move. The distances between them collapsed. Apply that logic to a chip. Take the logic components of a processor that would normally be spread across a single flat layer of silicon. Divide that logic into two halves. Stack one half directly on top of the other. Components that previously communicated across millimeters of flat silicon now communicate across the tiny vertical distance between two adjacent layers. Millimeters become microns. The signal journey shrinks by a factor of 1,000. When the journey shrinks, the delay shrinks. When the delay shrinks, the energy consumed by each communication shrinks. When energy consumption shrinks, heat generation shrinks. And when you can do all of those things simultaneously without changing the transistors themselves, you get significantly more computing capability from the same manufacturing process. Huawei calls this tau scaling. The name references the Chinese concept of time, specifically the time signals spend traveling rather than the time transistors spend computing. Their early implementations show a transistor density of 238 million transistors per square millimeter, approximately 55% higher than their flat chip design, using the same underlying manufacturing process. Their roadmap projects that by 2031, this approach could deliver performance equivalent to what the industry would describe as a 1.4 nanometer chip, without EUV, without ASML, without any of the tools the restrictions were designed to permanently remove from their reach. Before you decide what to make of that claim, you need to understand one specific number buried in the technical details of the announcement. Because this number is where the entire credibility of what Huawei is claiming either stands or falls. 1.5 microns. This is the bonding pitch Huawei is targeting for the connections between their stacked chip layers. And to understand why it matters, you need to understand what happens at the boundary between two stacked chips. The two layers have to communicate constantly. Every calculation requires billions of signals to pass between them every second. The connections that carry those signals are tiny copper contacts bonded directly from the surface of one layer to the surface of the other. The smaller those contacts can be made and the closer together they can be placed, the more connections you can establish and the more freely information can flow between the layers. The spacing between those connection points is the bonding pitch. The current world best in commercial production is approximately 9 microns. That is what AMD achieves in their three-dimensional V-Cache technology, currently the most advanced commercial implementation of chip stacking available anywhere. TSMC and Intel are working in the same range. Huawei is claiming 1.5 microns, 6 times smaller than the current global benchmark. Going from 9 microns to 1.5 microns is not a refinement of existing techniques. It requires new materials for the bonding layer itself, new equipment capable of placing those materials at the required precision, new process chemistry for forming the bonds, new testing methodologies for verifying at scale that the bonds formed correctly given that individual failures at this scale are impossible to inspect directly. The kind of advance that the industry would normally expect to require a decade of progressive improvement is being presented as a near-term target. Here is why this number is the one that matters above all others. At 1.5 micron bonding pitch, the density of connections between the two stacked layers is high enough that they stop behaving like two chips communicating with each other. They start behaving like a single processor that occupies two physical layers. The seam between them disappears from a performance standpoint. The full vision of what folding the chip promises becomes achievable. At 9 microns, the two layers are communicating well, but the bandwidth of the connection limits how completely unified they can behave. At 1.5 microns, that limitation largely disappears. The 1.5 micron claim is where the proof of concept ends and the proof of reality begins. Now, the complication that the announcement created more questions about than it answered, heat, not as a general concern, but as a specific and fundamental physical challenge that sits directly in the path of everything Huawei is describing. Logic chips generate enormous amounts of heat. Every transistor switch, happening hundreds of billions of times per second across the chip, releases a tiny pulse of thermal energy. Aggregate across hundreds of billions of transistors running continuously, and you have a component that generates heat at a rate requiring active and continuous cooling to prevent self-destruction. In a data center environment, this is manageable. Liquid cooling loops, dedicated airflow systems, buildings designed around thermal management. The infrastructure exists and it works. In a smartphone, it does not exist. A smartphone chip operates within a thermal envelope defined by what a human hand can tolerate on its surface. The entire thermal management system is a thin piece of metal and a graphite heat spreader. Everything the chip does has to fit within that constraint. Huawei's primary target application for tau scaling is a Kirin processor, a smartphone chip. When you stack one hot logic chip directly on top of another hot logic chip in a smartphone, the heat from the bottom layer has nowhere to go. The top layer is sitting on it, generating its own heat and blocking the path that the bottom layer's heat would normally escape through. You have created a thermal trap in the most thermally constrained consumer electronics environment that exists. No major commercial semiconductor manufacturer has solved this for logic-on-logic stacking at the density Huawei is targeting in a mobile application. Research exists, laboratory demonstrations exist, production-scale solutions with commercial yield do not yet exist publicly. This is not a reason to dismiss what Huawei announced. The history of semiconductor engineering contains problem after problem that looked physically insurmountable until someone solved it. The thermal challenge in stacked logic chips may be added to that list. Or it may prove to be a genuine ceiling that limits the approach to applications where more robust cooling infrastructure is available. What matters is being honest about the fact that the announcement addressed the concept compellingly and the thermal management solution incompletely. The full significance of what Huawei is claiming depends on a problem they have not yet publicly demonstrated solving. Here is the context that almost no coverage of this story provides. Huawei is not the only organization thinking about chips this way. The direction they are pushing in is a direction the entire industry was already moving, just more slowly and through more incremental steps. AMD already stacks memory on top of logic in their processors. The three-dimensional V-cache technology adds a layer of cache memory above the processor die and produces performance improvements significant enough to have made it commercially important. High bandwidth memory used in NVIDIA's AI chips stacks up to 12 memory layers on top of each other. Intel's Foveros program and TSMC's SoIC program both involve vertical chip stacking, and both are actively developing towards smaller bonding pitches over time. The industry was already building in the direction of folded chips. What makes Huawei's announcement distinct is not the concept. It is three specific things. The first is the attempt to stack logic on logic rather than memory on logic. Memory chips run cool, logic chips run hot. The thermal problem in logic on logic stacking is significantly harder than in memory on logic stacking, where the cooler memory layer can actually help conduct heat away from the logic below it. Nobody is doing logic on logic stacking commercially at the density Huawei is targeting. The second is the 1.5 micron bonding pitch claim. If achieved, this would be a genuine world first, 6 times beyond the current commercial benchmark, and would change the competitive picture in advanced chip packaging across the entire industry. The third is the context. Huawei is attempting this not as an optional enhancement to a chip portfolio that includes access to conventional scaling paths. They are attempting it as the primary path forward because the conventional paths are blocked. The necessity is real, and the engineering response to that necessity is what makes this specific announcement different from everything else in the chip stacking conversation. Here is the question that the announcement forces into the open, that nobody who designed the export restrictions fully answered. The theory behind controlling access to EUV lithography was that lithography is the choke point. Control the light source that prints the transistors, and you control the transistors, and therefore the chips, and therefore the applications. The theory treated the path through EUV as the only viable path to competitive chip performance. What tau scaling suggests, if it works, is that the theory was incomplete, that there is a path to competitive chip performance that does not require printing smaller transistors at all. That the performance gap the restrictions were designed to make permanent can potentially be closed through an architectural approach rather than a manufacturing process approach. This is more significant than it might initially appear, because if there is one architectural path that bypasses the lithography choke point, there may be others. The restrictions were designed around a specific theory of where the choke points in semiconductor technology are. If that theory is wrong or incomplete, the restrictions achieve something less than their designers intended. America built a wall. The wall is real. The constraint it imposes is real. The costs it has created for Chinese semiconductor development are real. None of that is in question. What is now in question is whether the wall was built around the right room. The engineers in Shenzhen appear to have found a room the wall was not designed to enclose. Whether that room has everything they need to build what they are claiming is a question the next 5 years will answer. What the announcement has already proven, regardless of how the technical questions ultimately resolve, is something that the designers of the restrictions did not fully account for. When you tell a sufficiently motivated and sufficiently capable engineering team that something is impossible, you do not always get the outcome you intend. Sometimes you get tau scaling. The roadmap Huawei published extends to 2031, 5 years from now. In the semiconductor industry, 5 years is enough time for the entire competitive landscape to shift multiple times. What to watch in the near term is specific and trackable. The first signal will be yield data from SMIC on the bonded chip layers. A chip that performs brilliantly in a laboratory prototype but fails commercially because the percentage of working units per wafer is too low to be economically viable is not a product. It is a proof of concept. The transition from proof of concept to product requires yield that only comes from solving the manufacturing challenges that show up at volume. When reports emerge from supply chain sources about SMIC's yield on bonded chips, that will be the first meaningful data point about whether the roadmap is grounded in manufacturing reality or engineering aspiration. The second signal will be thermal data from any Kirin chip that ships using stacked logic. The surface temperature behavior of a device containing stacked logic chips under sustained workload will tell you more about whether the thermal problem has been solved than any announcement or roadmap document. Benchmark data combined with thermal measurements will answer the question the announcement left open. The third signal is the response from the rest of the industry. If 1.5 micron bonding becomes real and manufacturable, TSMC, Intel, and AMD will accelerate their own programs in response. The pace of that acceleration, visible through patent filings, equipment orders, and product announcements, will be an indirect measure of how seriously they are assessing Huawei's progress. Here is where we land. America said it was impossible to develop competitive chip performance without access to EUV lithography. The confidence behind that statement was genuine and grounded in a real understanding of how the established path to chip advancement works. What China built in response was not a path around the restriction. It was a path that does not intersect with the restriction at all. An architectural approach to chip performance that treats the distance between transistors as the variable to optimize rather than the size of the transistors themselves. The early results are real. The concept is serious. The 1.5 micron bonding pitch target is where the genuine frontier of the claim sits and where the genuine test of the claim will occur. The thermal challenge is real and unresolved at commercial scale for the mobile application Huawei is targeting. The honest summary is that the announcement represents serious engineering aimed at a real problem through a genuinely novel approach. Whether it delivers on its full roadmap by 2031 is unknown. Whether it delivers on enough of it to meaningfully change the competitive picture before 2031 is a question that the next 12 to 24 months of manufacturing progress will begin to answer. What has already been established, regardless of how those questions resolve, is the part that the title of this story describes. America said it was impossible. China found a different definition of possible. And the room where that happened is in Shenzhen. And it is still running. If this gave you a genuinely deeper understanding of one of the most consequential technology stories unfolding right now, hit the like button before you go. It makes a real difference to whether this reaches the people who want to think seriously about these questions. Subscribe and turn on notifications because this story is going to produce significant new developments and you want to be there when they land. Drop a comment and tell me what you actually think. Does Huawei solve the thermal problem in time to ship a stacked Kirin chip before 2028? I read every single one. See you in the next one.